Hello everyone, the topic of this presentation is pore-scale simulation of methane transport in complex nanopores using a stabilized lattice Boltzmann method. And I'm Liu, a PhD student at University of Wyoming. I'm presenting this work on behalf of my co-authors, Dr. Wang, a former PhD student in our group and a current postdoc at TU Delft, and Dr. Ariana, our PhD advisor at the University of Wyoming. And this is the outline for this presentation. As we all know, there are two important gas flow characteristics in shale pores. They are slippage and adsorption. And I will illustrate how to couple these transport characteristic and phase behavior by using lattice Boltzmann method, and how to implement this LBM to slit and complex shale pores, benchmarked against MD results. So first, why do we use LBM to simulate nano-sized pore? As clarified by Newton number, methane flow in nanopores are often in slip flow regions or transition flow region, where the continuum-based approaches may not be valid. And LBM is a particle-based approach which focus on the distribution function of particles. In LBM, distribution function is discrete on lattices with many moving directions. And in our model, we use D2Q9 model. It means 2 dimensions and 9 velocity directions. And the distribution function will be affected by collisions and external forces at that lattice. And then, after delta t, the new distribution will stream to next lattice according to its velocity direction. And the adsorption behavior is controlled by the external forces. In this system, there are two kinds of interaction forces. One is a force between fluid and fluid, the other is between fluid and the wall, or we can see between fluid and solid. And here, a parameter is introduced, pseudopotential psi. You may think of it as effective mass. In this model, fluid particles in the lattice will be subjected to the forces from neighboring lattices, and the neighboring fluid and solid lattices decide interaction types. And after calculating the interaction forces with neighboring 8 lattices, we can calculate the resultant force now. And the result and the adsorption behavior is represented by this resultant force. So, how do we calculate this pseudopotential? Different equation of state lead to different forms of pseudopotential. So we need to have a suitable equation of state for nano-confined pores. And in this work, we use Peng-Robinson equation of state, which is widely used to capture the phase behavior of methane in nanopores, and this equation of state is shown on the top of this slide. You can see two important parameters A and B, which are associated with attractive and repulsive forces. And by combining PRUS and the relationship between pseudopotential and pressure, we cancel the pressure term to obtain the pseudopotential as a function of density. And thus, we are able to calculate the intermolecular forces and represent the adsorption behavior now. And we know the value of parameters A and B in physical space. In LBM, however, flow is simulated using a different other set of units, lattice units. In lattice units, in addition to A and B, we have two additional parameters, G, F, W, and R, which also contribute to the degree of freedom of LBM. And according to our simulation, we found that the thickness of adsorption layer is mainly controlled by the value of A in lattice units rather than B, and the adsorption density is mainly controlled by the value of GFW. So following this, we build up a workflow to tune the free parameters in LBM and match the reference MD results in slit nanopores. First, we find the constants A and B for the scenarios of interest with the fixed lattice length, and we ensure that this set of constants are able to handle the desired simulation pressure. And second, we adjust the fluid wall interaction force parameter GFW to account for the adsorption force under various pressure faithfully. And the three figures on this slide show the normalized density distribution under different pressure. For clearly comparing with reference MD data, only half of the distribution function or distribution are presented here. And in step number 3, we adjust the combination coefficient R to control the proportion of bounce back versus specular reflection. This enables accurate representation of transport near the wall. We are able to adjust the slippage velocity to match the mass flux profile from the reference MD data, and the mass flux is a product of the velocity and density here. And after that, we calculate the contribution of viscous flow, Newton diffusion, and surface diffusion by their area in mass flux profiles. So first, we change the pore size at 10 megapascal to match the flux contribution with reference MD results. It shows good agreement with MD results when pore is larger than 4 nanometers, and then we change pressure at 6 and 10 nanometers, and all the results show good agreement on the different pressure. So finally, we use the model to simulate transport in rough nanopores, in complex nanopores, which have boundaries with complex geometry. We divided the boundary lattices into 12 types as shown in the upper right figure on this slide. And we obtained the SR direction by considering the normal direction of the physical boundary shape rather than the boundary geometry in the LBM computational domain. For example, some typical SR direction at a concave boundary point are shown in the lower right figure on this slide. And then we simulate scenarios with complex geometry. We must also include regularization to the simulation algorithm. In original discretization of LBM, only the equilibrium part in distribution function can be projected onto the subspace, spanned by the leading second order of Hermite orthonormal basis, and the non-equilibrium part cannot. And the regularization is a process of ensuring that the non-equilibrium distribution function can also project it onto the subspace. So this process provides higher accuracy when simulating complex geometries. For example, the left figure on the bottom shows the simulation domain. According to the figure in the middle, we can see that the all figures on physical distributions of the velocity profile appears in the steady-state solution when we do not use regularization. And to alleviate this, we add regularization. However, the addition of regularization seems to result in a lack of convergence to the correct density rate distribution to steady state. For example, in the same simulation domain at the cross-section nx equal to 3, the density at the position 5 becomes negative during the simulation. It's approaching the equilibrium state from the initial conditions. And so based on this, we proposed a precondition method which considers the algorithm without regularization serves as a preconditioner for the one with regularization. And that is, initially we do not add regularization and get the steady-state solution for the complex nanopores as shown in the left of this slide. And then we use the steady-state solution as the initial condition and use the algorithm with regularization and run simulation to achieve a new steady-state solution. As shown in the right, this results in a physical steady-state solution. And we also validate the method by changing the relative roughness and shape of obstacles in the pore. The relative roughness RR is defined as the ratio of the height of the obstacle over the pore width, and the steady-state solution of mass flux profiles are shown on the left. And from the right figures, it is observed that the geometry of the surface roughness can impact the transport behavior, although this impact is not as pronounced as the size of the obstacle relative to the characteristic length of the flow pathway. And the last, if you want to see more details, you can see you may see this paper, Insights into Scale Translation of Methane Transport in Nanopores. And last but not least, this work is supported as part of the Center for Mechanistic Control of Water Hydrocarbon Rogue Interaction in Unconventional and Tight Oil Formations, funded by the United States Department of Energy. Thank you. That's all.